Hello everybody, thank you for joining me today. My name is Willem and today we're going to be covering nuclear fission. So a couple of our learning objectives are to define nuclear fission and to understand the process of nuclear fission. So if you're ready, let's get right into it. Okay, so what actually is nuclear fission? Well, nuclear fission can be described as the process of a large nucleus absorbing a neutron and then splitting into several daughter nuclei. Okay, so let's have a look at this in an actual real term. So we have here our large nucleus, which is uranium-235. Now this absorbs a neutron here, and so it becomes a heavier version of uranium-235 called uranium-236. The fact that it's heavy is represented by the increase in mass number, and an increase of 1 shows you that it's 1 extra neutron. Now, this heavier element suddenly becomes unstable. Okay, it's unstable because all of the forces in the atom are suddenly imbalanced, right? You're adding something on, you're sort of like tipping the scales. Okay, this scale tipping is unsustainable, right? Nothing in nature wants to be unstable. So to become stable, it's the larger nucleus splits into several daughter nuclei. In this case, barium-144 and krypton-89. Now, generally, the daughter nuclei are evenly weighted, right? So the heavier elements kind of splits evenly, but when it's but usually that's not really the case. So to account for imbalances is right, because not everything in nature can split cleanly in half. You also get three neutrons, like a 3 to sometimes even 5, 3 neutrons also released. Remember, the conservation of mass tells us that the mass of products must equal the mass of the reactants. In this case, that's just the one uranium-236 nucleus mass of reactant. Yeah, that's what I'm going to leave it to. Okay, so now these three free neutrons can then go on to back to other uranium-235 molecules, and then they can cause those to split again, and those to split again into 2 daughter nuclei plus 3 more neutrons, and so the cycle continues. And really, and so this ends up having a chain reaction, right? So one fissile reaction, so one fission, so one nucleus splitting into smaller nuclides gives off neutrons. Those neutrons then go and attack another nucleus. That nucleus splits. They release even more neutrons, and so on and so on and so on. So you sort of get a domino effect. Now, in nuclear reactors, this chain reaction is controlled. So let's write that down. Nuclear reactors, chain reaction is controlled. Okay, yeah, so I forgot to mention that when this larger nucleus splits into smaller nuclei, a tiny bit of mass is actually lost. That mass is converted into energy by Einstein's famous equation that E equals mc squared, right? So really, in the equation, we also have plus energy. Okay, so in nuclear reactors, this chain reaction of atoms splitting up and releasing energy is what we use to chain reaction is controlled and then used to heat water. So when we heat water, it turns into steam, and then the steam can be fed into turbines to produce electricity. But in nuclear bomb, these chain reactions are uncontrolled, so you have a huge amount of energy released in a very short amount of time, which is what causes the explosion. So the real difference between a nuclear reactor and a nuclear bomb is the fact that nuclear reactors are controlled using control rods. That's something that we're going to be looking at throughout another video as well. Now I have here the part of a nuclear reactor that's the most exciting, right? Where all of the actual fuel actually is, where all of the nuclear stuff actually happens. So this is called a boiling water reactor, and it kind of really just looks like a plain old boiler, and that's actually what a nuclear reactor really is. Whereas a normal boiler uses gas or electricity to heat up water for your home, a nuclear reactor uses a nuclear fuel, which is where the fuel elements are. So let's label that straight away, where the nuclear fuel is, uses nuclear fuel and the power of fission, or rather the energy released when fission happens, to boil water and so it turns into steam, which then gets pumped to a turbine, and the turbine spins to generate electricity. So let's work our way through the entire workings of a nuclear reactor. So here we have water entering into the actual vessel itself. Now, here where the fuel elements are, that's where the nuclear fuel resides. And then we have something special called control rods. So these control rods are very special because these control the rate of the chain reaction. Now, if you remember earlier on in the video, I told you that when one nucleus absorbs a neutron, it splits into several daughter nucleuses and a few free neutrons. Those free neutrons then go on and get absorbed by other nucleuses, and so those nucleuses also split. They split into further daughter nuclei, and they release even more neutrons, and so on and so on and so on. So you get a chain reaction. When the chain reaction gets so too far, so let's actually do it up here a bit. If chain reaction gets too fast, control rods are lowered. Now, what does that do? So control rods absorb neutrons. So now that they're absorbing neutrons, that means that there aren't any neutrons for the fuel to actually absorb. So the fuel can't break down into daughter nucleuses, so it can't release more energy, and so it can't release more neutrons as well. And so the chain reaction starts to slow down. Now, why would you want to slow down the chain reaction in the first place? Well, that's because a too high of a chain reaction leads to too much energy being released, and so the entire thing is at risk of blowing up, like the Chernobyl incident. So now you really understand the functioning of a nuclear reactor, which is really just fission products release energy. They cause a chain reaction, which turns normal water into steam, which then goes to a turbine, and the function of control rods, which are really neutron absorbers, which can be lowered and raised to control the rate of chain reaction in a nuclear reactor.